In the previous video, we saw that in many situations, we're going to need to sample items from a population because it's going to be just plain impossible to study all members of that population of interest. And now in this video, we're going to show what is the implication of doing so. Let's go through an example to illustrate. Let's say that we're interested in the days to recover for patients. And just for the purpose of illustration, let's imagine that this is what the distribution looks like. And we are interested in the mean time to recover. So let's call it mu. So the purpose of our study is to figure out, on average, how many days it takes for patients to recover. What do we do? Well, as we saw, we draw a sample of patients, and then we record the days to recover of those patients. So let's say we draw a sample of 30 patients, let's say x1 all the way to x30, and we compute the sample mean of those 30 patients. So that's going to be x bar. And then what we do is estimate that the mean in the population of interest, the mu, is going to be what we observe in our sample, x bar. So more technically, what we say is that mu hat, if you see this hat over here, that means we are estimating mu. So an estimate for mu is going to be the sample mean. And so the problem here is that there is a certain degree of error, of course, because we don't have all members of the population. We just have 30 of them. It's going to be a little bit of error. And the thing is that if we only have one sample, if we only have one sample of 30 patients, how much error do we have? Well, we have no idea. Let's imagine that we draw a sample of 30 over here. This is what everything looks like. And we see here in blue that we are slightly overestimating the true mean time to recover in red. Let's say we have a different set of 30 patients, another sample. Then it could look like this. It's very close to the real value, but still overestimating a little bit. Let's say we got access to another 30 patients, and the distribution looks like this. In this case, we are underestimating the true mu by a little bit. So you see, depending on which specific sample we have, because normally this is just a random sample from the population, we're going to have a certain degree of variation. We are never going to observe the exact mu. We're going to observe mu plus minus a certain amount of error. And let's say that we are lucky, we get to study 100 different patients in one take, in one sample. Then what we see here is that the estimation is actually very good. It's very close to mu. And that leads a little bit into the idea that the more data we have, the better. Let me illustrate even more. So in this case, we are estimating the mean performance of an algorithm, which is measured between 0 and 1. And again, we have no idea what the distribution looks like for the population, but just for the sake of argument, let's pretend it looks something like this. So the whole point of the study is to estimate the value of that mu. Again, we draw a sample of 10. Here we are underestimating a little bit. Another sample, overestimating. Another sample, underestimating. By quite a large amount, right? Let's say we go for 30 observations. So the number of observations per sample is 30. We carry out the study and we have this estimation over here. It's still underestimating, but a little bit better. What about another set of 30 observations? It looks closer, another one closer. Let's say we go for 100. So instead of samples of 10 observations or 30 observations, we go for 100. Then what we have is we're very close to it, very close to it, very close to it. And so the idea is that, again, we're trying to estimate a certain quantity, let's say the mean, that is fixed. We have no idea about it. And by studying a sample, we want to estimate it with the sample mean. The thing is, because we have a random sample from the population, we have a random amount of error, random error. And that leads right into the sampling distribution and the standard error. So the point is, let's assume that we are trying to estimate this mu from some distribution that we have no idea about, but we want to estimate the mean. Again, the experiment is draw a random sample of size n and compute the mean. What we call the sampling distribution of the sample mean is the distribution that it would follow over replications of the experiment. So again, let's say we want to study this population. We have no idea what it is about, but we want to estimate this mu, which in this case it's equal 4. Then what we could do is, let's say from here, we draw a sample of n items. And then from there, we compute the sample mean. Let's imagine that we could repeat this process and sample another set of n observations and compute the mean. Let's pretend that we could do it again all the way to xn, and we have the sample mean. And we continue. So the question one could ask ourselves is, well, what is the distribution of these sample means? So that is not the distribution of one specific observation, but the distribution of the sample of n observations. That is the sampling distribution of, in this case, the mean. And so here over the right, we have what the sampling distribution would look like for different sample sizes from 10 to 100. And what we see is that the sampling distribution of the mean is centered around 4, which happens to be the true mean. We will see in some other video why this is the case. But then imagine that we go only for 10 items, so a very small sample size. Then here in the most light green, we have what the sampling distribution of the mean would be. And what we say is that it's very wide. So with only 10 items, we could expect the sample mean to have a large amount of error because we don't have enough data. So on average, we expect it to be around 4, but any given sample, any one experiment of sample size equal 10, it could vary quite a lot. If we increase the sample size, let's say we go for 50, then the distribution will be this one over here. It looks a little bit better. It's a little bit narrower, which tells us that if we move from 10 observations to 50 observations, we are expected to be closer to the true value, closer to the mu equal 4. And if we go for even more, let's say 100 over here, then we are even narrower in terms of the sampling distribution. And so for any given experiment of sample size 100, we are expected to get even closer to the true value of 4. And if you realize, I'm all the time saying expected, because again, for just one sample, we have no idea how close we are. We could estimate it, we're going to see a little bit about it, but we have no idea. It could be far away. The thing is, we are expected to be close. And very related to the sampling distribution is the standard error, which is just the standard deviation of this distribution. And so what that tells us is if the standard error is high, then the statistic, in this case the sample mean, could vary quite a lot. If the standard error is small, then that means the distribution is not expected to vary too much. So in principle, whenever we want to estimate anything about a population, it could be the sample mean, the variance, the maximum, or any other statistic, the standard error of that statistic is going to tell us how much error should we expect, how much random error we should expect in estimating that statistic from a sample of a certain size. And that's exactly what we want. We cannot study the population, we can only study a sample, find how much error should we expect. That's precisely what the sampling distribution is telling us. So the important point here is that it's not just for the sample mean, it's for any statistic that we should be able to compute from a sample. And so let's say we wonder about the sample variance. Well, it also has a sampling distribution that looks a little bit different from what we saw earlier. It's actually this one over here, but in principle, we could compute it. So in this case, it's going to be concentrated around 7 because the variance of the population is 7. And what we see is that if we have only 10 observations in a sample, we see here in light green that there is a lot of variability. The standard error is high, and so we should expect a lot of random error when estimated only with 10 observations. If we go all the way to 100, we see that the distribution now is a lot narrower, standard error is smaller, and therefore we should expect to have a small random error when estimating this variance. And so the sampling distribution tells us how much random error we should expect. just from the sampling process, because we cannot study all the population. How much error should we expect in the first place? Again, conditioned on the sample size. And so the standard error is very simple to quantify this. It's the standard deviation of this sampling distribution. It depends, of course, on the shape of the data distribution. It depends, of course, on the specific statistic we want to estimate. We have no idea what it looks like, but we can estimate it. That is the point. And so if a sample produces a statistic too extreme under the sampling distribution, then it can suggest that the underlying process doesn't behave like we think it does. So we are studying a certain process, certain phenomena, and we surely have a certain hypothesis for how it works, and we want to test it. Now, under that hypothesis, we should be able to define what the sampling distribution of those statistics looks like. And if we actually carry out our experiment, our study, and we collect the data, we look at it, we compute the statistics, and they turn out to be very extreme under this sampling distribution, then that's an indication that our hypothesis might be incorrect, because our data is very extreme under that hypothesis. So let's say if we have the hypothesis that the variance is 7, this is what the sampling distribution looks like. If we actually collect the data and turns out that our measurement is something like 15, then that's a very clear evidence that it's not 7, it's probably something larger. So everything in statistical analysis is about comparing what we expect given certain hypotheses and what we actually observe and comparing those two. And from there, we're going to be able to say whether there are effects or not. Let me just continue to a couple of misunderstandings that we see very often. The first one says that a random sample is always representative of the target population. Well, no. If you think about it, all samples of size n are equally likely to be drawn, even those that have very rare items, or even those that have observations that are very unlikely under the population. We only have one sample. We could just be very unlucky. We don't know. We have no idea. If we have no idea what the population looks like and we just draw a sample, there's no way for us to say, hey, this sample is representative or not. Maybe we just get unlucky. Just think about a coin. We know that if we toss a coin, we should expect half the times heads and half the times tails. But I'm sure that if you start flipping the coin and you see that maybe one time out of 10 times that you do it, 8 of them were heads. You just got unlucky. Or you just got lucky, depending on what you're trying to prove. So the point is, we don't know. What can we do about it? Well, we should always try and check the characteristics of our sample if we can. If we know that the population has certain characteristics, then we should always try and check that our sample also has those characteristics. If we can, we should always replicate, so draw more samples so that we are sure that we just didn't get lucky or unlucky in a previous experiment. The point is, this process of randomly sampling from a population is expected to be representative over replications of the sample process. Given just one sample, we don't know. And the second misunderstanding is this one that says something like a sample size of 30 is sufficient. Well, no. It turns out that n equals 30 is the point in which the sampling distribution of the mean is sufficiently close to a Gaussian for practical purposes. We don't need to know the details now. But the thing is, it depends on the minimum effect size that we want to detect. It depends on what is the effect that you expect, how large it is, and how much variation there is in the sample to begin with. How much variation do we have in the data? What should we do? First of all, try and run a preliminary study and do power analysis. We will see what power analysis is in a few videos. But the idea is that we should try and collect a little bit of data first to get a sense of what the data looks like. And based on that, make a decision as to how many observations we are going to need to be more certain that we detect a certain effect. And always search for clues in the literature. Search for characteristics of the target populations. Maybe someone studied the population you're interested in some years ago, and you might find some clues as to properties or what the data looks like. And you, based on that, could make a decision as to how many observations you are going to collect.